Hello everyone, our team name is Hakuna Matata. My name is Huang Yushan.
My name is Lin Zhiyu.
My name is Hu Tingyi.
In the beginning, we would like to introduce the algorithms of our design. To find the average every run, at first, we need to know how many bits there are when 8 input data are added with each other. Because there are 128 bits for one data, the sum will up to 131 bits. Next, to compute the average of the sum, it should be divided by 8.
Next, let's talk about the algorithm of min and max functions. For starters, we compare the first 8 bits that are close to MSB of two input data. Then, we compare every 8 bits starting from the MSB until the end of the two data. When A is larger to B or B is larger to A, a positive edge trigger will be generated at the input port of the flip-flop. The out signal is sent to the flip-flop, and the maximum and minimum values are selected through mux and output to another register. Then, this maximum or minimum value will compare with the next input data. This will repeat for 7 times in order to complete a round. Peak maximum or minimum function is similar to minimum or maximum. We output and store the maximum or minimum value in the first round in another register when count is equal to 8. And this maximum or minimum value will compare with another maximum or minimum output in the second round. If the second output value exceeds the value of the first round, we output the result. Otherwise, we won't send out data.
INO is the algorithm of extract and exclude. As we know, the function of extract is to output a value which is larger than 6 and smaller than 10. And the function of exclude is to output a value which is smaller than 7 or larger than 11. And we can draw these two diagrams to show all possible results of these two functions.
Let's introduce the structure of our design. To compute the average, as you can see, we set a counter here to initialize register A, which is used to store the value output by the adder every time. And the new data will input register B per 8 bits during a clock cycle. After 16 clock cycle, two of the value in register A and register B will add with each other and store back to register A. After 96 clock cycles, the sum will be transmitted to a shift-right register one by one bit. Finally, to compute the average, the sum should be shift-right 3 more times. For 132-bit adder, we consider to connect 8 16-bit Brancon adder and a 4-bit full adder. Because our design target is to minimize the area, and Brancon adder is one of the parallel prefix adder, it has high speed and minimum area.
To introduce our architecture of min and max function, the basic components that we design should be clearly introduced. The two 4-bit comparators can do the comparison of two 8 bits and output the result of 3 status. We can see that only when the two data are equivalent will the equal bit be sent to 1. Since the input will send 8 bits in a cycle, to minimize the operation time, we can compare the first 8 bits that are close to the MSB until the end of the 128 bits of the data. When we get the result of A larger to B or B larger to a positive edge trigger will be sent to the input clock port of the D flip-flop in order to send the result to the mux. The output of the mux will then be stored in the register, waiting for the next stage comparison. Furthermore, with the feedback circuit that we design, once there is a zero appears in the equal bits, that is, once there is an inequality, the circuit will lock the state in order to make our result be stable regardless of the possibility that the later comparison of the following bits might be different. Not until we count out that our comparison cycle has ended will the state lock circuit be reset. In addition, Mux will receive the data with the main result being the one from Q plum and the max result be the one from Q. With one run having 8 inputs, we will repeat the comparison of 8 times and restore the maximum or minimum value in the register every time. When we reach the last stage, we then output the result. Peak min and peak max is similar to the previous one. After we output the first result, we restore it to another register and compare them with the next round.
Next is the structure of extract and exclude. First, we use two mux and function select bit to choose the upper bound and the lower bound. Then we use another mux to select whether we want to compare the input with the upper bound or the lower bound. And we input the two values into the 8-bit comparator. Then we can use the two output from comparator to check whether the value need to be compared again or not, and also check whether we need to output the value or not. If the value need to be compared again, the try buffer will let the next compare result input and check it again. If the input fits the condition, the value will be output. Next is the known and to be learned issue. The issue we need to learn is that because our design target is to minimize the area, the fact that the registers we use in our design would cause larger area. So the first issue we need to solve is the waste of the storage space. And the other issue is that because we want to minimize the area, so we need to use a large number of clock cycles, which will cause the execute time of our design become larger. Next is a to-do list of our group. After this class, we need to watch all groups' video and create our final structure. Then we need to write the first edition code and run synthesis. Before the second presentation, after the presentation, we want to optimize our code and circuit. Then we can finish our final report. This is the member job assignment of our group. This is the project work schedule of our group. Final is the possible issue and expected solution. First is the structure of maximum and minimum. If the input A is equal to B, then the value of equal will always be 0, and this causes the signal input to D flip-flop always be 1, which can't generate any positive edge signal to trigger D flip-flop to output the value Z. And the solution we expect is that we want to use a counter with a smaller period of clock cycle to initialize the value to 0, which needed to input to the flip-flop. And the second possible issue we think is that the output may not the same with what we expected. And the solution we think is to write each function in submodule and compile each of them to debug. And this is all of our presentation. Thanks for your patience.